The Rolls-Royce Trent XWB stands as one of the most formidable jet engines in the world, delivering an awe-inspiring 97,000 pounds of thrust. Notably, it's the driving force behind mammoth aircrafts like the Airbus A350-900 and A350-1000. The entire assembly process takes place in Derby, England, and begins as a collaborative global effort from the design teams specializing in various aspects of engineering and production. These teams, located worldwide, delve into intricate design considerations, taking into account everything from the overall structure of the engine to individual components and even post-production service requirements. They approach the engineering challenges from multiple perspectives, based on their specific roles within the supply chain. Once the comprehensive design phase is complete, the complex yet methodical assembly process begins. At the heart of this intricate assembly process is the fan disc, which serves as the foundation for the engine's fan blades. In addition to the blades, specialized annulus fillers are inserted between each blade to optimize airflow. With the fan assembly complete, attention shifts to the engine's rear components, with the turbine and the shaft. The turbine blades are engineered to spin the shaft, which is mechanically linked to the fan. Simultaneously, the low-pressure turbine at the engine's rear is carefully constructed in a vertical orientation. While this is underway, the previously assembled fan is positioned within a specialized casing replete with a maze of wires and piping. To avoid any errors, technicians rely on detailed computerized schematics to ensure that each wire and pipe is precisely where it should be. When the engine core is complete and the fan has been accurately placed within its casing, the two are integrated into a process referred to as marrying the components. The fully assembled engine then moves on to a stringent testing phase. Within a state-of-the-art testing facility, the engine is suspended mid-air and anchored to a platform for comprehensive performance evaluations. Controlled from a dedicated command room, the engine undergoes a battery of tests, simulating extreme conditions. Among these is the water ingestion test, where thousands of gallons of water are pumped through the engine to assess its resilience against severe weather conditions. Additional tests include the fan blade-off test, designed to determine the engine's structural integrity by deliberately fracturing a fan blade. This test ensures that even in the event of a blade failure, the remaining system retains functionality. Bird strike testing replicates the common hazard of bird collisions during flight, validating the engine's durability under such circumstances. Perhaps the most arduous of these trials is the cold start test. A large refrigeration unit encases the Trent XWB, lowering its temperature substantially. After a 24-hour freeze period, technicians attempt to start the engine, simulating the challenges of initiating flight under extreme cold conditions. Upon successful completion of these tests and subsequent approval from the relevant authorities, the Rolls-Royce Trent XWB engines are deemed ready for installation into aircraft, marking the culmination of an intricate process blending engineering brilliance with rigorous quality assurance. The GE9X115B engine served as a paradigm shift in the aviation industry, primarily due to its groundbreaking use of carbon fiber composite fan blades. Building on this legacy, General Electric GE revolutionized the aviation landscape once more with the introduction of the GE9X engine. Announced in 2012, this engineering marvel was designed to propel the Boeing 777X series. Remarkably, the engine features only 16 fan blades, each fashioned from 4th generation carbon fiber composites that are slimmer yet more resilient, wider, and longer than their predecessors. The GE9X sets an unparalleled standard with its compressor boasting a 27:1 compression ratio, effectively turning the engine into an industry game-changer. It also incorporates an advanced lean-burning combustor capable of withstanding the highest temperatures ever encountered within a jet engine. To bring these innovative components to life, GE harnesses the capabilities of 3D printing, enabling the fabrication of parts previously deemed unattainable. Moreover, the use of ceramic metric composites, which weigh merely a third as much as their metal counterparts yet offer twice the strength, paves the way for a quieter, more fuel-efficient engine, thus underlining GE's commitment to greener technologies. Once the engine's core was completed at their Jupiter, Florida facility, it was transported to Avondale, Ohio. The core was installed into Test Cell 44, a specialized environment where rigorous testing protocols were executed. Before the GE9X could be integrated into the Boeing 777X, it had to successfully complete a series of icing tests. Impressively, the engine cleared the 162 testing cycles and received approval 7 months ahead of schedule. For financial certification, the GE9X was moved to a state-of-the-art testing facility in Peebles, Ohio, where it underwent further rigorous evaluations beginning in May 2017. Upon successful completion of all certification tests, the engine was mounted onto a Boeing 777X. The maiden flight took place on January 25, 2020, and lasted for a noteworthy 3 hours and 52 minutes, marking a significant milestone in both GE's and the aviation industry's ongoing quest for excellence and innovation. The F-35 Lightning II stands as a pinnacle of modern military aviation, epitomizing stealth and power in a single $75 million package. Propelled by Pratt Whitney's F-135 low-bypass augmented turbofan engine, this airborne behemoth has set new standards for fighter jet capabilities. Although the F-135 is an advanced iteration of Pratt Whitney's F-119, which powers the F-22 Raptor, its distinct features make it uniquely suited for the F-35. While some F-35s were initially equipped with GE's F-136 engines, these are no longer in production, making the F-135 the primary focus of our discussion. The journey of the F-135 began in the 1990s when Pratt Whitney meticulously presented their initial designs to government contractors. Engineers laboriously drafted each component, compressor, combustor, and turbine on paper before turning to advanced computer simulations for optimization and virtual testing. Their compelling proposal eventually won them the contract in 2001 under the Joint Strike Fighter (JSF) program, which aimed to unify various military branches through a shared aircraft model. To bring their intricate designs to life, Pratt Whitney partnered with specialized third-party manufacturers, employing cutting-edge techniques like additive manufacturing, 3D printing, and precision machining. These facilities crafted the complex components that would come together to form the engine. Recognizing that even minor delays could disrupt the entire production line, Pratt Whitney established a centralized command center to meticulously track the 45,000 different parts involved in the assembly process, from sizable components to minuscule screws and bolts. Once the engine's core, including the compressor, combustor, and high-pressure turbine, was assembled, subsequent phases saw the addition of the fan and low-pressure turbine sections. The fully assembled engines were then subjected to rigorous evaluations in specialized facilities known as hush houses. Located across the United States and one in Japan, in places like California, Florida, Texas, Virginia, and Maryland, these hush houses are designed to minimize noise pollution while optimizing airflow, providing a controlled environment for a battery of performance, stress, and environmental tests under extreme conditions. Should the engines pass all stringent standards, they are then integrated into the F-35 airframes during the final assembly at Lockheed Martin's facilities. However, this isn't the end of the line. The aircraft must still undergo a comprehensive set of final checks, including engine integration evaluations, avionics testing, and a myriad of other system tests. Only upon the successful completion of these final reviews is the F-35 deemed ready to join the fleet, reinforcing its reputation as one of the most advanced and formidable fighter jets ever to grace the skies.